All right. So we'll go into our linked list. We're going to write a method here, public int count, because this guy's going to return the number of elements in the list. Right off the bat, the trivial case is if head is equal to null, return 0. Nothing in the list. All right, so that's the easy case. Else, well, if head equals something, we at least have one element in the list. So we'll start off at 1. We'll make cur point to the same place head points to. Then while cur dot get next node is not equal to null, as long as we still have another element, sum plus plus, and cur is equal to his own next node. And then in the end, return sum. If it's the empty list, return 0, easy case. Otherwise, it's not the empty list. We must have at least one element in it, so we'll start sum off at 1. We'll create a node pointer to point to the very same place as head points to, so at least the front of the list. And then as long as cur has another node, has somebody after it, we'll increment sum, because we found another node, and then we will traverse the list, cur. So cur will become whatever cur's next node was. All right? In the end, we'll return sum. So looking at our example here, we added 3, 7, and 4. So we should have 3 elements in the list, right? System.out.println ll.count. We get our 3. Go ahead.
Can you add the question things on angle for like the 1, 2, 3, and 4 for when we submit homework?
Question things.
Like the things we're supposed to answer. You know what I'm talking about?
So like, for instance, if I had asked you to write this for your homework assignment,
yeah. You know,
give you this input and say what the output should be?
No. You know how like when we submit homework, you usually have the homework assignment like thing that we have to fill out with it.
Yeah.
It's not on Angel. So he didn't know he had to do it. Yeah. And he doesn't know the sequence that you have to do.
Oh, that's not on Angel?
No.
Really? Oh, you get a 0. I didn't know that wasn't on Angel. I'm sorry.
Everybody else just has a copy.
Well, at least this assignment was simple, right? How many of you struggled with the homework assignment? I expect most hands to be up. Right, so no struggle, piece of cake. Yeah, I agree.
I would have hoped.
Why do you think I had you guys do it? I can't solve this crap. All right, how many? So most of the class struggled with it, right? How many of you spent at least 2 hours on the assignment? Okay. Who spent at least 1 hour on the assignment? So I see a couple of hands that a couple non-hands, people who said, yes, I struggled, but I spent 15 minutes on the homework. All right. I would have expected for this assignment, you would have spent at least 2 hours on the assignment if you struggled. Okay? If you ran into problems and you hit a wall, then you need to ask for help. Okay? Don't just keep hitting the wall and assuming that you're just an idiot. Okay? All right. So let's go ahead and write the answer to the homework. So it was add front, correct? All right. So Add front means we're taking in a payload, we're creating a brand new node, and we're going to add this to the front of the list, as opposed to what we did before where we added things to the end of the list. All right, so regardless what happens, we're always going to create a new node out of our payload, just like we did for addEnd. Okay, then the trivial case, if head is equal to null, if I currently have the empty list, then I'll just set head equal to n, and I'm done. Make sense? That's if we're adding to the front of the empty list. Similarly, we could have actually just called addEnd in that case, because they both do the same thing. If you're adding to the front or adding to the end of the list that contains nothing, the resulting list will be the same. Correct? All right. So these are the simple cases. Notice that the simple case for add front is the same as the simple case for addEnd, which is the same as the simple case for count, which is the same as the simple case for display. Okay, so linked lists start with the pointer for head, because we have to traverse the list to get to any content. Well, if head doesn't point to anything, we're done. So just say the appropriate thing. If we're displaying, say the empty list. If we are adding to the front, make head point to the new guy. If we're adding to the end, make head point to the new guy. Make sense? If we're counting, the count is 0. There's nothing in this list. All right, so that's our easy case. Otherwise, there is something currently in the list. Now, you should be drawing pictures when you are solving these problems. This is extremely helpful when dealing with linked lists. I had a heavy breakfast, excuse me. You're going to take credit for it?
All the coffee on the guys.
All right, so for instance, let's say we have the list. Let's say we have the list 1, 2, 3. And these guys are all connected to each other. All right, and then of course we have our variable called head. And head is going to point to the beginning of the list. So each of these blue boxes is a node, and head points to the very first node in the list. Okay, and now we're going to add a new node, 4, to the front of the list. Very first thing we ask is head equal to null? It's not. Head currently points to something real. So that means we need to add something to the list. Well, to add to the front, I ultimately want my list to look like this. That's the ultimate result that I want. Make sense? I want to add 4 in front of all these other elements and make head point to the 4 point to the 1, and everything else points to the same place it used to point to. That's what I want to happen. So let's back up here for a second. Put our list back to its current state. All right, so head is not equal to null. So what are we going to do first? Well, we cannot set head equal to this new node yet. Why not?
Then you will know what it was pointing to.
Yeah, we've lost the old list. It's floating out there in the middle of nowhere. We have no way of getting to it. That makes sense? 1 still points to 2, 2 still points to 3, but nothing points to 1. So we can't actually get to that list anymore.
So that's because the node sets the next node to null in our node class.
No, I mean, it's because of how this picture looks. If head, the only way I can get to this guy is through head, right? If I make head point to something else, if I change the value of head to be this guy, nothing currently points there. Does that make sense? He's going to get garbage collected. And when he gets garbage collected, nothing's going to point to 2. When 2 gets garbage collected, nothing's going to point to 3. See the problem there? Okay, we have to, linked lists rely on these links to maintain to stay in contact. That way we don't lose portions of the list. Right now we have a list sitting out here. We have a hotel that has no roads that go to it. Make sense? So we can't just set head equal to our new node. Instead, what we're going to do is we're going to set our new node's next pointer to point to the same thing head points to. Then we will change head. So we maintain the link to 1 before we broke, before we change the value of head. So we're going to say n dot set next node is equal to head. We're going to make n's next node be the same thing as head's next node. So now our list is in this shape. That's what it looks like right now. Head and n both point to the same place, which is the old front of the list. Make sense? Then we're going to set head equal to end. Done. That's the whole homework assignment. Go ahead.
Do we need the if-else statement?
Do you need the if-else statement?
As if there was nothing, use that next node to add, it would just be.
That's true. So if we didn't ask is head equal to null, and we set n's next node equal to head, it's redundant because it's already null. So he's saying we actually could have just put this code right here and been done with it. It's a true statement. I tend to like the implementation that has the if-else in it because I think it's clear. If it's the empty list, just make head point to it. Otherwise, do this. That make sense? But they're functionally equivalent. In your example, what we would do is we would overwrite a null with a null. All right, so that the second line was to do this. Now we've effectively added 4 in front of the old list. Make sense? So I come into driver. Let's get rid of the count thing real quick. Right now we're adding end 3, 7, and 4, and we'll go ahead and display that. We get 3, 7, 4 because we originally added 3 to the end, then we added 7 to the end of that, then we added 4 to the end of that, so we're stuck with 3, 7, 4 in our list. Now, let's say ll.add front a 2, and then we'll display it again. Now we should have 2, 3, 7, 4. Should be our new list. Make sense? All right. Questions on how that works? Now, in the end, the solution looks pretty simple, right? Go ahead.
Why does setting n to head again not just override the whole thing?
Okay, why does setting
Like,
head equal to n?
Yes, why is setting head equal to head?
Okay. So if we're sitting in this position right now, are you good with this position? Okay, so we set n's next node equal to the same thing head points to. So now we're in this position right here. You want to know why does doing this not break it?
Right.
Okay, tell me why you think it would break it.
Because I was just getting that on the assignment.
No, I get that, which is extremely normal. Remember last semester when I first introduced pointers? I made a comment that pointers are actually very easy, but it's something that most beginning programmers really struggle with. It's hard to wrap your mind around. And when we draw these little pictures like this, it seems so easy. Like, oh, that just worked. But it is supposed to be difficult. Okay, so I guess I'm asking the question of you right now is if I take head is a variable. Okay, we want to think about what head is because head is a node just like n is a node. So let's go ahead and give ourselves this variable called n. All right, so we initially created a brand new node called n. So we have this variable value pair right here. Okay, now n is a pointer. And what's a pointer? Holds a memory address. So n's value is actually a memory address. And that memory address is the memory address where this node actually lives in memory. That make sense? Okay, so n's value is not a node. N's value is a memory address, which points to a node. Similarly, head say that's that memory address. Head's value is a memory address. It is that memory address that is said to point to a place in memory. So in this little example here, this node 1 lives at memory address 1308, somewhere in RAM. Okay? So when we created this variable called head, head's value, when we set head equal to that, when we first added to list, when we set it equal to n, we set head equal to the memory address where this guy lives. So head is holding 1308, a memory location. When we set n's next node equal to this guy, what we're doing is n has within it a variable called next node. And we're setting that guy equal to 1308. And it's that guy that points to the next node in memory. Okay? So this is just like if I were giving you the address to my house, or giving you inviting you to a party. I need to tell this node how to get to this node. So rather than setting next node's value equal to the actual node, which would be equivalent to me handing you my house, we instead set next node equal to the address where we can find the node that holds a 1. Okay? So are you kind of getting how pointers work? They hold memory addresses and that's it. These guys here, these nodes, are floating out in memory regardless of the pointers. Okay? They're out there. They're actual physical objects, just like a house is a physical object. If I want to tell you where you can find my house, I give you a pointer to it. I give you the address where you can find that house. I give you the address where you can find the front of the list. Front of the list currently lives at 1308. But the new front of the list is going to be at memory address 221. And because I've connected the correct dots, once you get to this house, he will have the information you need to get to this house. Once you get to this house, he has the information you need to get to this house. Who has the information you need to get to this house? Who knows that he's at the end of the line? Because his next pointer, this guy, for this dude is null. Currently points nowhere. And that gets back to what you were saying when we first create a node. We set that node's next node by default to null. So all nodes, when they come into existence, when we first create a node, like we did right here, node n equals new node payload, what that does is it creates for us something like this. A node object that lives somewhere in memory. So let's say this guy lives at memory address 87. Okay, how do we know it lives somewhere in memory? Because it was created using the new keyword, which is our real estate agent, who went out and found a memory address, a big enough plot of land to build one of these guys. Okay, so when we built that node N, we created a new object located at memory address 87. So that object actually got built. And we stored the address of that object inside of a variable named N. So after that one line of code there, we have something that looks like this. So we have access to this node, but that's it. This node doesn't point anywhere real. It's just a node floating out there in memory, and if at any point in time we change the value of N and disconnect it, so nothing points here, that node will be automatically garbage collected. The memory will be recaptured. But as long as I maintain this pointer, I have an anchor, I have a rope, a lasso around this node that I can now get to it and manipulate it in different ways, as in I can add it to the front of the list by making it point to the same thing that head points to. So now I have two separate pointers that point to the front of the list. One of them is head, and one of them is this node's next node variable. And we said that this guy is 1308, right? Oh, did we give a memory address to this dude in any of my examples? 250 something? Let's just say it's that. So head currently held 255 because it was pointing to the front of the list, which is this is the memory address of this guy. Now next node, we set N's next node is now pointing to the same place as head points to. So we have two separate node variables that have the exact same value. That value is the memory address 255, the memory address 255, which is said to be a pointer, that's why we drew these pointing arrows, to a place in memory, that is the memory address 255, where this actual node lives. So now I have two separate variables that point to the same place. N does not point to this place. N points to here. This node's next node pointer is what points to this guy. So the two things that point to this node up here right now in this picture is head and N's next node. Now that I have another pointer to this guy, I can change head to point here, which means changing head's value to 87. So now head points to the same place N points to. N's next node points to the place head used to point to. This node points to this guy. This node's next node points to this guy. This guy's next node points to this guy. And this guy's next node points to null. Does that make sense?
More than it did.
Huh?
More than it did.
Okay. So do you have, now that I've done that, do you have follow-up questions? See, my theory is when students start thinking about memory, we immediately assume things are more difficult. Memory is just a value.
So when I was doing the homework,
Mhm.
I found, isn't this built into the language?
Yeah, I told you that last time, but you're not allowed to use it.
Yeah.
Eventually, I'll let you use it when we go and do something else even more difficult. But right now, we have to build our own. So what else? Okay. Now, what if, let's just drag N off to the side here. Let's just get some of these things out of the way. What if I want to create a new node let's say this guy holds a 7. And let's say I want to add this guy somewhere in the middle of this list. If we treat this list kind of like an array, where this is bucket 0, this is bucket 1, this is bucket 2, this is bucket 3, this is bucket 4, if I treat it like something like that, and let's say I want to add this guy so that his position is bucket 2. Right now this is 0, 1, 2, so I want this guy to be the new bucket 2, which would then lead to this guy, which is the new bucket 3, bucket 4, bucket 5. Make sense? So I want to add it somewhere in the middle of the list. That is not to the front of the list, not to the end of the list, but to a significantly more complex place in the list, which makes us update even more pointers. Go ahead.
Wouldn't you just do what we did kind of like for the homework? What, you go to a certain point where you want it and then do that?
Well, you wouldn't do the same thing. So if we're going to draw the picture here, if we're putting this guy here, and we want him to essentially be where this guy is right now. So I said 0, 1, 2, oh, where this guy is, where the 1 is. We're putting it at bucket 2. That means I need this guy to point here, right? But what just happened? I lost this list. So I want this guy to point here, then this guy to point here. But how do I know about this guy? If I'm traversing this list, if I want 7 to be the new bucket 2, how do I know that I need to make 7 point to this guy?
Turn it into an array first.
I suppose you could turn it into an array first. That would be pretty inefficient.
That's my specialty.
That's my specialty. Like, okay, you want to build a new car? First, we got to piece this thing out. No, you want, what is it? You want to, let's say you want to add a radio. So we're going to add a radio to this car. We're going to disassemble this thing. Get it down to its bare parts. Then we're going to go pick out a radio. Then we're going to put it all back together. But before we do that, we're going to actually put it into another car. All right, so who knows about this node? This guy. So in this entire world right here, the only guy that knows how to get to this guy is that guy. So to get to node 2, I have to first go to node 1. And if I'm at node 1, I can make node 1, well, I can make my new node point to the same place that node 1 points to. That is node 1's next node. That make sense? So to replace this guy, I actually have to go to the position right before him. And that way I can ask this guy to tell me, who do you point to? And I will set my pointer to the same place. Then we can make this guy point there. We've maintained our connections through our list. That make sense? All right, now before we write that, we're going to write a little helper function that may or may not directly help us with this problem, but it's going to give us something similar. We're going to write a get method. And what this get method is going to do is we're going to say, get me the value at a particular position in my list. So if I say, get me the value at index 0, it will return a 5. as an int. If I say get me the value at position 1, it would be a 4. Position 2, a 1, 3, 4. That make sense? So this allows me to get a value at a particular bucket in the linked list by traversing the list. So we're going to write get first. So we're going to have public int get. And this guy's going to take an index as a parameter, the index that we want to get. All right. So in this example out here, if I say get 0, the element at bucket 0 is the element that head points to. So that should return a 5. If I say get 1, it should return a 4. What if I say get 30? It's an error. Why? There is no bucket 30. How do you know? Count. We wrote a function called count that tells us how many elements are in there. And for this guy, what would count return for this particular list? 1, 2, 3, 4, 5. 5 elements in this list, right? Okay. And what are the legal indexes of this list? If it's got 5 elements, it's 0 to 4. 0 to 4. Okay. So the biggest value that index can be is what? Count minus 1. What's the smallest value index can be? 0. So right off the bat, we can say int count is equal to this dot count. This is a local variable named count, and we're calling a method called count, which tells us how many elements are in this list. Make sense? In a little bit, we'll make this a little bit more efficient, because right now, every single time we need to know how many elements, we are counting the entire list, traversing the entire list, where we already have some methods that tell us every single time something gets added to the list. When we're adding front, doesn't the list just get one bigger than it used to be? If we're adding end, doesn't the list get one bigger than it used to be? So we could have a running total somewhere, right? For right now, we'll use our count. All right, so count is the number of elements in the list. If index is greater than or equal to count, we have an error. Correct? Or index less than 0, we have an error. So for right now, let's just print out a little error message. We'll say system.err.println. This is the error stream, so it'll show up in red in Eclipse, as opposed to system.out.println. You can say system.out if you want. It'll just, all we're doing is displaying crap to the screen. And we'll say illegal index. All right. So this is if count is greater than or equal to, or if index is greater or equal to count, or if index is less than 0. Or what else would be a legal index? So if the index they pass us is too big, it's bigger than count, if it's less than 0, or if what is true. What happens if I try to access any bucket in the empty list? So we have a list with nothing in it. Can I access bucket 0? No. Is this going to be an error at this point, as I have it written right now? I can pass in a 0 and we're still cool. I want to say this is also an error if we're trying to access any index of the empty list. Heads equal to null. So if index is greater than or equal to count, or if index is less than 0, Or if head is equal to null. Now think about this for a second. That's two equal signs. Does index greater than or equal to count cover that situation? If we have the empty list, what's the count of the empty list? 0. So even if index is 0, even if we pass it as 0, would that be illegal in this case? Is 0 greater than or equal to 0? So that's a true statement. With ORs, only one of these needs to be true. So this will fire an illegal index, right? So do we need this? This covers it for us. If count is 0, meaning there's no elements in the list, and we pass in, we want bucket 0, or bucket anything for that matter. Okay, but if we pass in bucket 0, 0 is greater than or equal to 0. Therefore, this will be true, which is bad news, so we'll print out an illegal index. Go ahead.
Is there any real difference between null and 0?
Well, sure. 0 is a numeric value. Null is an empty pointer, an empty memory address. So in this case, count is returning for us the primitive int, which is the number of elements in the list. Where checking to see if head is equal to null is checking the pointer, the node pointer head, to see if it points to nothing. Does that make sense? Now, having said that, if you want to mentally think about null as being the object version of nothing, the object version of 0, I think that's a fairly accurate way of thinking about it. You just can't do math with it. Okay? All right. So, if whatever index I passed in is too big, illegal index, or if it's an illegal index in all cases, that is less than 0, illegal index. Otherwise, we must be looking at a legit place in the list. Okay, if we're looking at a legit place in the list, that means that index is a legal place in the list. Well, so how am I going to get to position index in my list? Okay, well, before we talk about the for loop, generally speaking, how do I get anywhere in a linked list? I have to traverse the list. Okay? If I need to get to this node in this list, I can't just go right there. I start here. I find where the beginning of the list is. And I go from this guy using his get node method to get to this guy. And I use his get node method or get next node method to get to this guy. Then to get to this guy. Does that make sense? So I have to traverse the list to get anywhere in the list. Now, if I'm looking at node 2, 0, 1, 2, how many times do I have to loop through the list? Or how many times do I have to traverse? I start here. Let's traverse once. Now we're at bucket 1. Let's traverse twice. Now we're at bucket 2. 2 traversals to get to position 2. How many traversals to get to position 0? Well, if I start at the beginning of the list, do I have to go anywhere to get to position 0? Nope. 0 traversals. So you mentioned a for loop. How many times is this for loop going to go through? For int I is equal to 0, I is less than, if I want to get to bucket 2, I is less than index I plus plus. So if index was 2, I'll go through on 0 and I'll go through on 1. 2 times. Okay? So this is the number of times I'll go through. And what do I want to do each time? We look at our picture here. I need to get to this guy. If my example is I want to get index 2. So if this is my current list, we can get rid of this guy for a second. If this is my current list and I want to get to bucket 2, what do I need to do? I need to start at the beginning. What does it mean to start at the beginning? Yeah, cur. I need to create another pointer. Maybe you call this guy cur. I will make cur point to the same place as head points to. We can't just use head and move head around because we'll break the front of the list, right? So we're going to need a second pointer to start off pointing to the same place head points to, and then move from next node to next node the correct number of times. So before this loop, we'll set node cur is equal to head. So now we have a second variable called cur that holds the same memory address that head currently holds. They both point to the same place in memory. All right? They're not linked to each other. They just happen to both hold. It's like me and Nick having a piece of paper that has the memory address of a pizza place on it. Okay? If Nick decides to go to a different pizza place, that doesn't affect my destination. Make sense? So we both have an address, but those are separate addresses that just happen to go to the same place. Okay? And that's what we have right here. Me and Nick, both holding the memory address of this pizza place. Make sense? All right. So that's what we start off with. That's how I get to that value right there. Node cur is equal to head. Now, this is the number of times I need to traverse the list. That is the number of times I need to update cur to be his own next node. In our example here, I'll set, if I want to get to 2, bucket 2, I'll set cur's next node equal, I'll set cur equal to his own next node, which takes me to here. That's once. Then I'll set cur equal to his own next node, which takes me to here. That's twice. And now I'm pointing at bucket 2. Huh?
Will it let you go to 2?
Yeah.
Because your index is 2, isn't it?
Yeah.
But that's
0,
fine.
1.
Yeah.
Yeah, it just won't go the third time. So we'll say cur is equal to cur dot get next node. Okay? And then here, cur currently points to the right node. This guy's going to return an int, so I'm going to return cur dot get payload. That is the value that lives within the node that cur currently points to. All right, now up here, we currently have an issue. That is, we're printing out that there was an illegal index, but we're not actually returning a value. This method requires us to return a value, or we can throw an exception. Okay, for right now, just for testing, I'm going to return a -1 here. Then we'll return it. We'll throw an exception here in a second. Okay, but this would be a good example of when to use exceptions, because returning a -1 really isn't very accurate, because are there any rules that say we can't store a -1 in our list? We could store the value -1 in our list if we'd like to. So the question is, if we have this error, is this -1 the payload -1 that was at our destination? Or is it the -1 that means you gave me a bad index, so I'm just throwing some number to make Java happy? Because if I don't return a value here, if I comment that out, notice that Java's upset. Get must return a result of type int. Right now, I only return an int inside the else. The if portion of this could potentially fail, and I don't return a value. Does that make sense? So in older languages, like C, C++, where we did not have exception handling. Now remind me, did we do exceptions at all last semester?
No.
Okay, that's fine, but we've seen it before. We've seen array index out of bounds exception where Java screams at us. Okay, we've seen that kind of stuff. Well, in older languages that didn't have exceptions, we really had to do something like this, have an error code, if you will. We've seen error codes. Go to a website and you get the HTML error 400 or 500 or something like that. So you get error codes that you can go look up on the HTML standards chart to find out what that means. Might say page not found or web server unreachable, that kind of crap. All right, but in this case, we have a conundrum, big word, conundrum. Okay, and that is what integer, since we have to return an int, what integer should we return to represent that there was a problem when any integer is fair game in our linked list? Make sense the problem? Can I do that? Well, this guy must return an int. Well, can I return null? No, that's not an int.
If you want to return the one that was causing the issue, wouldn't you just return whatever the index is that you input?
You could return the index if you'd like, but let's say the index was 2. Aren't we allowed to hold it? Well, didn't we have a 2 in our list? Are we allowed to hold the number 2? Does that mean, did we return the index 2 or did we return the value 2 that lived at the in the payload? See the problem? Okay, so in older languages, we had to have exceptions like that, but we had to handle them ourselves. We had to have the magical number that we returned. Maybe you returned some number that was completely beyond what would ever live in your list. Probably. You know, maybe you returned the largest integer or the smallest integer, -2 billion, let's say. And you just knew that -2 billion meant something bad happened. So you would, external to this method, whenever you called it, you'd have to check. If -2 or if -2 billion was returned, that means bad stuff went down. And I didn't get a real payload. I got my error number. Make sense? For right now, we'll just go ahead and we'll return a -1 as our temporary error number. So if we get a -1 out of this, we know that something went wrong. So we'll have to self-police ourselves and never store -1 on our list for the next several minutes.
Well, we just know because if we get a -1 but there's no illegal index, then we know that was...
Visually, we will visually know, just from our own print statements, but we wouldn't necessarily be able to handle that programmatically. But you're absolutely right. So we're going to do this kind of the getaway for 5 minutes or so, then I'll show you the exceptions. All right, so if something bad happens, we'll print it out, and then we're going to return a -1, and that is what it is. Otherwise, we're going to traverse our list to the correct place in our list and ultimately extract the payload from that node, so cur.getPayload, which will return the integer that lives within that node. Remember last time we used the setters and getters creation tool built into Eclipse to create a method for us called getPayloadInNode to return the payload, which is an int inside of our node objects. Make sense? All right. So that's what get does currently. So let's go out here to driver. And just to show us our list real quick, our current list is 2374. So if I say get 0, it should give me a 2. Right? So there's my get 0, and there's my 2. Get 1 should give me a 3. Get 2 should give me a 7. Get 3 should give me a 4. And get 4 should give me an illegal index error message followed by a -1. Notice the illegal index is displayed in red. And see how it's at the top here? System.err, the error stream, is a different stream than system.out. But there's our -1. And I'll just show that to you real quick. So illegal index is in red. If I come into linked list here, instead of doing system.err, I can do system.out. And now it'll just be in black. two separate output streams. One is for errors, one is for standard output. And that's really something left over from older languages. If we were programming out here at the terminal, and we had a program that was running, let's see. Let's see what's up. Okay, I think that's an error message. So if I say ls y star yep. So what I did is I redirected, that's what this right arrow is. I redirected on output stream 2. That's so in the Unix shell, this is the bash shell. In the Unix shell, we have the normal error stream, or the normal stream, which is 1. So for instance, I can do this. We'll call this normal.text. Okay, so notice that the error is still printed out to normal, the screen. And if I look at normal.text, there's nothing in there. Okay, as opposed to if I redirected the error stream, that is the second stream, to a text file called errors.txt, I got the error that was there. Now, that's because I created a situation where I said, show me all the files that start with a Y. And I have no files in here that start with a Y. Now, I do have files that start with a W. So I'll say W star, so I get real values now. So let's go up and let's run the same thing again. So instead of Y star, I'll say W star and redirect the errors. Okay, and we'll see that there's nothing in there because there were no errors that got displayed. Similarly, if I redirect the normal output to normal.txt from something that doesn't show an error, we'll see that nothing displays on the screen because I redirected what would have displayed on the screen to the file normal.txt. And there's the input. Does that make sense? So this is kind of giving a throwback to years ago when our programs were written for command line programming like this, probably in C or C++. And it would be helpful to differentiate between normal output and erroneous output. So they gave you options to put those on two separate output streams, so that if you needed to have the errors go to a log file somewhere and have the normal output either go to the screen or go to another file or wherever you wanted to put it, you had a way of dividing those two streams. Make sense? And that's why those exist in Java. So something you probably won't use very often, but something nonetheless. Okay. And similarly, let's say that I wanted to write, so we've seen several examples of our get method here. Let's say I wanted to display every element in my list. How could I do it out here? What would be the most efficient way, given what we've written so far, for us to display every element in the list? How many elements are in our list? Don't all speak at once.
4. That one.
How many elements are in our list? Usually when I ask the same question multiple times, it means your first answer wasn't quite what I was looking for. How many things are on our list?
Index? No.
I don't even see an index here. Count. Well, tell me more about that. How would I get the number of elements in the list? ll.count, called the method. The count method tells us how many elements. So there are ll.count elements in this list. And I want to display every one of those to the screen. How would I do that? Every one of those elements to the screen. Use a for loop. So for int I is equal to, what's the very first element? 0. And we're going to keep going as long as I is less than ll dot count, which really exaggerates how horribly inefficient this is. Because every single time through the loop, we're going to call that count method, and it's going to calculate how many elements are in that list every time through the loop. But we won't notice because computers are fast. And then we're going to print out what? I. All right, so this will go through every element of our list from bucket 0 all the way up to, but not including bucket count, getting each element and displaying it. So here's our display methods output 2, 3, 7, 4, and here's our loops output 2, 3, 7, 4. Make sense? And if you missed what I was talking about by the inefficiency here, remember how loops work. This part of the loop only gets only happens one time. Okay, once at the very beginning. This happens each time through the loop, and for loops are pre-check loops. So we ask this question right off the bat. Well, in order to ask this question, we're asking, is the current value of I less than whatever value is returned by the count method of LL? Well, the count method of LL goes through and literally starts at the beginning of the list and traverses the list from node to node to node, counting the number of times it was able to traverse. So that means every single time through this loop, we're going to traverse the entire list to get a count. That make sense? Probably not the efficient way of doing this. So if we wanted to make this a little bit more efficient, what could we do? We could come into linked list. We can add a private variable called count in here. When a list was first created, we can set count equal to 0 because there currently are no elements in the list. Then, inside of add front, so we in either of these cases, something got added to the list, right? We can say count plus plus, or this dot count plus plus if that makes you happier. I like being explicit. Similarly, in addEnd, whether we added it trivially to head or we actually did the work, we can add 1 to count. Make sense? So right now we only have 2 ways of adding stuff to our list, add front and addEnd. So now our count method, we can take all this stuff out and just return this dot count. Same output as it had before, but instead of calculating the count every single time we call the count method, we are now keeping track of a global variable called count. And whenever we add something to the list, we just increase count by 1. Similarly, when we start writing methods to remove stuff from the list, we'll have to decrement count. Make sense? So we need to keep track of when things are entering or leaving the list. And we'll see our output of this program is identical. Just trust me, under the hood, it's being more efficient because we're not traversing the entire list every single time when we call the count method. Right now, we're just returning the private integer called count. That makes sense? Okay. So we did not change the implementation of node. But we've added a couple of things to linked list. For your homework, we have add front, we have addEnd. We want to write add at index int payload. Okay, and this guy should add a node containing the payload such that this node will, and actually I need to add another element here. I'm taking in a payload and also an index where you want it to go. Add a node containing the payload such that this node will be added to the list and live at position index. That makes sense? For right now, any index, here, let's say, for now, and I'm going to give you this code. I'll copy this code in so you'll see this comment. For now, any index less than 0 should add to the front. Well, so let's say should add at bucket 0. Come on. Well, let's just say add at the front. Should add at the end of the list. Okay? So that is it, since I haven't shown you exceptions yet. If they give you indexes that are too small or too big, that just means that they want it either at the very beginning or they want it at the very end of the list. Make sense? This is due on Thursday. Similar to the assignment for today, this one's a little bit more complicated. Definitely draw pictures. Okay, it will help. It's not a hard assignment, but it should be challenging for you. But draw pictures and it'll be less challenging. All right, I'll see everybody on Thursday.